Hello everyone, my name is Bibin Abram, and in today's video we are going to talk about applications of Gauss law, and this is the first part of the video. In the next part we are going to talk about more of the application. So let's get started. So before I start today's topic, we need to do a quick recap of what Gauss law was. We have talked about Gauss law in our previous video. So basically, what was Gauss law? According to it, the net electric flux that is passing through a closed figure is actually 1 upon epsilon naught times the net charge enclosed inside that figure, right? For example, you guys can see, let's say if I have a plus q charge, right, and this plus q charge is enclosed inside a closed figure. Normally we call this closed figure as Gaussian surface. Gaussian surface. Now Gaussian surface and closed figure, we are actually talking about the same thing, right? So this is enclosed inside a closed Gaussian surface, right? So obviously this plus q charge, right, the electric flux will be going out from this plus q charge out through that Gaussian surface, right? So in this, in this example, the Gaussian surface is my sphere, right? This is actually a sphere, right? So mathematically I can write the net flux, that is E dot dA along that Gaussian surface, is actually equal to 1 upon epsilon naught times the net charge inside the Gaussian surface. So this is what is your Gauss law. Gauss law talks about the net flux that is passing through a closed surface or a Gaussian surface is actually given as 1 upon epsilon naught times the total charge that is enclosed inside your Gaussian surface, right? I hope that is understandable. So let's go to today's topic. Today's topic is electric field at various points due to a charged spherical shell. Okay, you have to understand, spherical shell will be our today's topic. So we are going to talk about electric field at different points because of that spherical shell, right? And we are going to use Gauss law to find that out, right? Okay, spherical shell, you have to understand, it's a shell. Shell means something which is hollow from inside. So basically it's a sphere, right? But it's not a solid sphere, it is hollow from inside. It's just solid from outside, right? So you have to understand it's hollow from inside. So for example, and it is charged. So if it is charged, then obviously all of the charge will be on the surface of the sphere. None of the charge will go inside because there is nothing inside to hold the charge. I hope you guys can see that, right? So in spherical shell, all of the charge will be on the surface of the shell, right? So I have a charged spherical shell and I'm supposed to find out electric field at various points due to this charged spherical shell, and I'm going to use Gauss law for it, right? So basically I'll be talking about 3 cases: case number 1, case number 2, case number 3. The first case is for a point A, there will be a point A outside the charged spherical shell, right? For a point A that is outside the shell, I'll talk about that, right? Second case is for a point B inside the charged spherical shell. Then we'll take a point inside the spherical shell and we will find out the electric field. And case number 3, for a point C on the surface of the charged spherical shell, right? And the last case will be that I will consider a point on the surface of the shell. So first case is a point which is like outside the spherical shell. Second case is the point which is inside the spherical shell. Third case is on the surface of the spherical shell, right? So let's get to it, right? Okay, so let's talk about the case 1, right? So case 1 is this one, for a point outside the charged spherical shell, right? So basically, okay, let me draw it and then we guys can understand that, right? So first case, all right, so basically this is my spherical shell. Let's say this is my spherical shell. All right, great. This is my spherical shell, and let's say this is the center, right? This center, let me call this center O, right? And let's say the radius of this spherical shell is capital R, right? I hope you guys can understand that, right? And it is charged, right? So it is charged, that means all of the charge will be on the surface because it's actually a shell, right? So all of the charge is at the surface, and let's say this has charge, some q charges there on the surface, right? Okay, great. Now we are supposed to find out, let's say I'm supposed to find out, let's say this is my point P. I'm supposed to find out electric field at this point P, right? And how I'm going to do it, right? So if you want to apply Gauss law, there must be a closed surface enclosing this shell, right? And like I said, we call that, surface Gaussian surface. So basically we will draw a Gaussian surface such that it will pass through my point P. It will pass through my point P. So what will be my Gaussian surface? It must be a closed surface. That means I'm going to draw a 3D figure. So one of the good inspiration that comes to my mind is that I should make a sphere, right? I should make a sphere which will pass through my point P, right? So I can make a sphere which can pass through my point P, and I can call that sphere as a Gaussian surface, right? Okay, let's make that thing, right? So I will make a sphere which will pass through my point, right? So there it is, right? So this is my Gaussian surface, which actually is passing through my point P, where I'm supposed to find out my electric field, right? And let me call this surface S1. This is my Gaussian surface S1, right? And let's say, you guys can see, let's say this distance is small r, right? So you guys can see small r is greater than your capital R, right? Small r is the distance between the center and to the point where you're supposed to find out your electric field, and capital R is to the center, to the sphere's radius, to the surface of the sphere. That is, that distance is your capital R, right? I hope that is understandable, clear, great. So I can write it here. Draw a Gaussian surface such that it enclose the point P, where we are supposed to find the electric field and apply Gauss law. Alright, so we have to now, next step is we have to apply the Gauss law, right? So how I'm supposed to apply the Gauss law? Obviously, see, just like we did in the previous video, the spherical case, I'm going to assume a small area here at point P. I'm going to assume a small area at point P. You can assume it anywhere, right? It does not matter. I can assume it here, I can assume it here, I can assume it here, anywhere on the Gaussian surface I can assume it, right? So obviously area vector will be coming out, which is perpendicularly out of the surface, right? And also because of all this positive charge, the electric field will be also in that direction. Yes or no? Electric field will be also, it will be also coming out, right? I hope you guys can understand that, right? So electric field is coming out, area vector is coming out. All I have to do is apply Gauss law, right? So according to Gauss law, mathematically I can write integration over a closed figure, and this time the closed figure is my sphere, the Gaussian figure, right? E dot dA vector, and that is equals to the net charge, that is enclosed Q total upon epsilon naught, right? I hope you guys can see that, right? Okay, now I can see E dA cos of the angle between your E vector and your dA vector, the angle theta is actually 0 degree, right? I hope you guys can see this is cos 0, right? This is Q total upon epsilon naught, right? Okay, great. And I know very nicely, I can see that your electric field is a constant quantity. At every point I can see this constant, so it will come out of my integration, and you'll be left with integration of dA, right? And that is equals to Q total upon epsilon naught, right? So let me complete it over here. So this will be electric field multiplied by, what is the area here? Area of the Gaussian surface we're talking, right? So area of the Gaussian surface is 4 pi, it's actually a sphere, right? 4 pi r square. Why r square? Because obviously I'm talking about the area of the Gaussian surface, right? 4 pi r square, and that is equal to Q. obviously the charge that is enclosing the Gaussian surface is q, right? You guys can see this is my Gaussian surface and there is q charge that is inside that Gaussian surface, right? So I can very nicely write q is the charge divided by epsilon naught, or the electric field at, you know, field that is, you know, coming out of it is actually q upon 4 pi r square times epsilon naught, right? So this is my answer, right? So I hope you guys can understand that, right? So for a point outside the you know, spherical charge, spherical shell, the electric field value is coming out to be E is equals to q 4 pi r square, q upon 4 pi r square epsilon naught, right? Or I can also see, you can also write this thing as E is equals to, you know, k q upon r square, right? And obviously direction is radially outward. You can actually write that radially outward, radially outward, radially outward, right? I hope that is understandable. Okay, great. Now if that is true, let's go to the second case. That was our first case. Let's go to the second case, case number 2. So what was case number 2? If you guys can see, case number, for a point inside the charged spherical shell, for a point inside the charged spherical shell. Okay, great. So I can, so for this one, obviously that this point is inside, so obviously r will be greater than the small r, right? So let's draw it and let's try to find out the answer, right? So this is my spherical shell. Let's say this is my spherical shell, right? And this spherical shell, all the charge, whatever charge is actually, it is on the surface, and let me say this is some q charge, that is, you know, that is a charge, right? Okay, so I'm supposed to, okay, all the labels, this is the center, let me call this a, this distance is r, right? And let's say I'm supposed to find out my electric field inside, right? Let's say let me take any random point. Let's say this is my point, right? I'm supposed to find out electric field. Let me call this point P. I'm supposed to find electric field at that point, right? Okay, how I'm supposed to do it, right? Again, Gaussian surface you have to make, right? So this time I will make the Gaussian surface inside such that my Gaussian surface include the point P, right? Great. So I will make a Gaussian closed surface, again a sphere which will include my point P. Yes or no, right? Great. So I got my Gaussian surface. So this is my Gaussian surface, right? Great. Now you have to understand here, do you guys see any charge inside? Do you guys see any charge inside? No, there is no charge inside, right? Keep that in mind, right? So I'll write that here, right? Draw a Gaussian surface such that it includes the point where we have to find the electric field, right? Again, you are going to use the same, you know, principle, right? I'm going to assume a small area, dA area, right? And this is my distance r, right? Obviously the r is where I have to, small r is where I have to find out the value of electric field, right? Which is like small r distance away, right? So from point P to the center, the distance is smaller, right? Okay, so I'll assume a small area vector, and then obviously area vector will be going out, that is your dA vector, right? So I can always apply the Gauss, that is E dot dA, right? And that is equals to Q total, that is the total charge that is enclosed inside a Gaussian surface, divided by epsilon naught, right? I hope you guys can understand that. Now, you know, by looking at the figure, you guys can see there is no charge inside, right? All the charge is at the surface. All the charge is actually at the surface, right? There is no charge inside, right? So that is something which is like problematic. There is no charge inside. So charge value is actually 0, right? So you guys can see this will become E dot dA, and the value of charge is 0 upon epsilon naught. So can I say this will implies that your electric field is actually 0? Yes or no? Electric field inside your spherical shell is 0 because because there is no charge inside the spherical shell, right? So from here I can conclude the electric field inside a spherical shell is 0. I hope that is understandable, right? Is that understandable? Yes or no? Great. Now let's move on to the third case. What was the third case? Let's see here. Third case was for a point on the surface of a charged spherical shell, right? So third case was, we will talk about case 3. For a point on the surface of spherical charged shell, right? For a point on the surface of spherical charged shell, that means your R will be actually equal to your capital R, right? I hope you guys can understand that, right? So let's make the diagram, right? So diagram is, this is your spherical shell, right? And let's say this is my center, right? This distance is capital R, right? Okay, great. Now obviously all the charges are on the surface, right? All the charges. Okay, let me this time let me make it here so that you guys can understand. It does not mean that it is inside, it's mean that it is at the surface, right? We have to assume that it is at the surface, it's not inside. Okay, it is at the surface, right? So all the positive charge is actually at the surface, right? So I can say Q charge is there at the surface, right? Clear? Great. Now I have to make the Gaussian surface, right? The Gaussian surface must include the point where I'm supposed to find out my electric field, right? And for this particular case, I will find out the electric field at the surface. Let me call at this P point I'm supposed to find out my electric field, right? Okay, then obviously I have to make the Gaussian surface, and Gaussian surface must include my point P where I'm supposed to find out my electric field, right? So this is my Gaussian surface, right? The surface itself become my Gaussian surface. I hope you guys can understand that, right? Great. Okay, so if that is true, tell me, does your R and small r, they become equal, right? This distance is both r as well as small r, right? Because obviously the sphere is same, right? I hope you guys can understand, right? Great. Now how will I find out? Okay, so you can just write it down, right? So this is my Gaussian surface. So I can write it, draw a Gaussian surface such that it includes the point where we are supposed to find the electric field. All right. Okay, great. So basically how you're supposed to find out, obviously the method is same. You will take a small area, right? This small area is dA area, and obviously area vector will be perpendicularly out, right? And obviously electric field also will be going out. Both will be making an angle of 0 degree with each other, right? So I can nicely apply Gauss law, that is integration over the closed surface E dot dA will be equal to the net charge that is enclosed divided by the epsilon naught, right? Great. So I can very nicely see E dA cos of 0 degree, right? Because the theta angle between my E vector and my dA vector is actually 0 degree, right? So I can write E dA cos 0, and we know cos 0 is actually 1, right? Is equals to Q total upon epsilon naught, right? So this will be equal to E dA cos is equals to QT upon epsilon naught, right? So basically your electric field will come out, because electric field is constant throughout, right? So it will come out, and this will be dA, and this is, see, the net charge that is inside is actually Q. Q is the net charge. You guys can see Q is the net charge, so I can write it Q upon epsilon naught, right? Or I can write it E multiplied by the area of the sphere is basically 4 pi r square, right? So this is 4 pi capital R square, because the radius of the surface, radius of the sphere is actually capital R, right? You can write it small r, but anyway capital R is same, right? Q upon epsilon naught, or you can write electric field comes out to be Q upon 4 pi epsilon naught times R square, right? Or I can write it E is equals to KQ upon capital R square radially outward, right? I hope that is so in the first case it comes out to be KQ small r square when your when your point P was outside the spherical shell, right? When it was inside, the value comes out to be 0, and when it was on the surface, the value comes out to be KQ upon capital R square, right? So based upon all these three results, I can actually make a graph which actually tells you how is, as the radius is changing, as the distance is changing, how the electric field is changing, right? So you guys can see for R less than your capital R, that means inside, when it is inside, electric field comes out to be 0. That means if this is my shell, right? If imagine this is your shell, this is the shell, right? And this shell has the radius of capital R, right? So if this is the shell, I can very nicely see, and this axis talks about the electric field, and this axis talks about the x-axis talks about the distance, right, through the center, right? From the center I am actually calculating, right? So inside the shell, the value of, you guys can see, the value of electric field is actually 0, right? Inside the shell, the value, let green green pen is actually representing the value of electric field. It is actually 0. This point is 0, 0, so it's actually 0 inside. The moment it comes, right, at the surface it becomes maximum. So you guys can see at the surface the value comes out to be KQ upon capital divided by capital R square. So at the surface it takes a value, so this value is E is equals to KQ upon capital R square, right? It takes a value, right? And as you go further away from the sphere, the value is reducing by 1 upon R square. You guys can see that it is getting reduced by 1 upon R square, right? So it's actually getting reduced like this. So your electric field is proportional to 1 upon R square as you move forward, right? I hope you guys can see that, as this graph actually shows you the comparison of how your electric field line is actually changing, right? So it's actually it is 0 for inside the shell, right? And it is as on the surface it becomes maximum, that is E is equals to KQ upon R square, and as you go forward it is reduced by 1 upon R square form, right? I hope that is understandable, right? So this is how, if you can make the graph, you can do a data kind of analysis based upon this graph, right? Okay, so this graph sometimes in exams also this kind of graph can be asked, right? So you guys can draw this kind of graph, right? Okay, one important note that we have to understand, right, before I end this video, the video is, in the case of finding electric field due to a charged shell outside, okay, so basically let's assume I have a shell, right? I have a shell, and obviously all the charge is on the surface, right? This is something which I know, right? So let's say at some r point I'm supposed to find out the electric field, right? So electric field, because of, and it comes out to be, if you guys see, some r distance, the electric field value is kq upon r square, right? So how much far, this is kq upon r square, the value comes out to be this, right? On the other hand, let's say if I had a point plus q charge, right, and I'm supposed to find out electric field at some r distance, again I would have got the same value, that is kq upon r square, right? So for both the cases I'm getting the same value, right? For a shell at r distance I'm getting the value of electric field to be kq upon r square. For a point charge I'm also getting the same. So what does this mean? This means that the shell, or the spherical shell SHELL, sorry, the spherical shell behaves as if the whole of the charge is concentrated at the center. Can you guys understand that? The spherical shell will behave as whole of its charge, although we can see the charge is kept at the surface, but we will feel that the charge is not at the surface but it is at the center, because you guys can see the result for both the cases are same. So we will feel like all of the charge is actually concentrated at a single point, that is at the center, right? And obviously we can use this concept to solve a lot of questions, right? So this concept is very important, right? You have to understand this concept, right? So I hope that is understandable, right? So I hope you understood the video. If you have any doubt, you can ask me in the comment section, and I hope all of you are doing good. Stay home, stay safe.